So in this session, we'll be taking up the questions of carboxylic acids and we'll be discussing the additional theory which we haven't covered. So the first question is the IUPAC name of the acid, and this is the structure given. So as we can see, there are two carboxylic acids which are directly attached to the parent chain and one is not directly attached. So in this, what we are going to do is we will number it from N, starting from carboxylic acid as the first. This will get 2, this will get 3, this will get 4, this will get 5, this will get 6. Numbering is done in such a way so that one with the side chain will get the lowest locant. So as we can see on the third positions, what we are having is, we are having for COH, the prefix we'll be using will be carboxy, and then we have a CH2 group for which we can use methyl. So we can name it as carboxy methyl, which is at third position. So it will be 3 carboxy methyl hexane, because the word root is for the 6 carbon chain will be hex, and it is -1,6 dioic acid. So the answer for this question will be option 2. You guys already know the rules for the nomenclature of carboxylic acids. So second question is, in which of the following sequence of reactions C is the product of reaction? So if you recall, this is an alkyl benzene. Now with alkyl benzene, if we use a strong oxidizing agent KMnO4 OH-, so here after KMnO4 OH-, this is representing that oxidation is done in the basic medium. So if we are taking toluene and if we are treating it with a strong oxidizing agent, then it will lead to the oxidation of the side chain, that is hot alkaline KMnO4 will convert it into benzoic acid. But we are not going to write benzoic acid, as the medium is acidic and an acid cannot remain protonated in the basic medium. So first, treatment with KMnO4 will lead to the oxidation of this carbon to the carboxylate group, and later protonation of this will generate our carboxylic acid. So I can say there is a step missing here which you can add from your side, that is after oxidation you will have to protonate it also to get benzoic acid. So we can say toluene is oxidized to benzoic acid using hot alkaline KMnO4. So this is our A. Now a carboxylic acid, when treated with thionyl chloride, we know thionyl chloride is actually used for replacing an OH group by a Cl group. So I hope there you can answer what will be the structure of B. B is going to be an acid halide, or we know that a carboxylic acid can be converted into acid chloride by using thionyl chloride, PCl3 or PCl5, out of which this one is the most preferred one. So we are having an acid halide, and this reducing agent, if you collect from the carbonyl chapter, that is aldehyde and ketone, you will understand that this is Rosenmund reduction, which actually reduces the acid halides to aldehydes. So here COCl will be reduced to CHO, and therefore the C will be benzaldehyde. So this is a very general reaction sequence where toluene is first oxidized to benzoic acid, for which we then converted benzoic acid into acid chloride, and then acid chlorides were reduced to benzaldehyde using Rosenmund reduction. So answer is option A. Next is a hydrocarbon C6H10 decolorized bromine water and gives cyclohexane on hydrogenation. We know for a 6 carbon, the number of hydrogen that we should have should be 14. That is, for a saturated hydrocarbon or for alkane, the formula is C6H14. To us, the compound that is given is C6H10. This is the hydrocarbon that is given to us. So if I find out degree of unsaturation in this, then I know a difference of 2 hydrogen is actually responsible for 1 degree of unsaturation. So if I see how much is the difference in the number of hydrogen from the saturated hydrocarbon and divided by 2, I will actually get what is the degree of unsaturation. So in this case 4 by 2 will be equal to 2, and this compound contains 2 as the degree of unsaturation. So very clear from this example that 2 degree of unsaturation, what 1 degree of unsaturation means. 1 degree of unsaturation means it can be a double bond or it can be a ring. So 1 double bond or 1 ring suggests 1 degree of unsaturation. If you write the molecular formula for this, you will get it as C6H12. So this cannot be my organic compound. If you write molecular formula for this, you will get C6H14. This cannot be my given compound. Whereas only for option A, you will find out that its molecular formula comes out to be C6H10, or degree of unsaturation here is 2 because it contains 1 ring and 1 double bond. So that is one way to eliminate the other option. Next will be adipic acid. Adipic acid will be, you can say, oh my son, go and play, and if the N value, because I have told you dicarboxylic acids have general formula CH2N, COH, COH, where N value here is 0, 1, 2, 3, 4, 5. So for adipic acid, you know, there will be 4 CH2 groups in between. So I can say if this is 1 COH, there will be 1 CH2, second CH2, third CH2, fourth CH2 and COH. So this is going to be the adipic acid. So let's see whether this alkene on oxidation gives adipic acid or not. We know oxidation using KMnO4 under hot condition is going to oxidize this bond in such a way so that it will bring the oxidative cleavage. So here if I write, this is this carbon, the one which I have marked it as star, will be oxidized to carboxylic acid. This is this carbon, and this carbon will also be oxidized to carboxylic acid. So this carbon is this one, this carbon is this one. You have already learned the oxidative cleavage of double bond using strong oxidizing agent like acidic KMnO4 or hot alkaline KMnO4. So this will also give, see if the number of CH2 group 1, 2, 3, 4. There are 4 CH2 groups, so this is our compound A. Plus they are saying that it decolorizes bromine water. That means you need to have a degree of unsaturation, that is a double bond should be there, and it gives hydrogenation, hydrocarbon, and if I put H2 across it, then I will get cyclohexane. Whereas this particular compound is already cyclohexane, so that cannot be our organic compound. So there are number of hints given in this question, you can just choose any one of them. Next is CH3C triple bond CH reacts with C2H5MgBr. So if you recollect, I already said while discussing the carbonation of CO2, I discussed the use of Grignard reagent. I said whenever we have Grignard reagent, it's considered to be a source of carbon ion. So for example, if I am having CH3CH2MgBr, then I can actually assume it as a source of CH3CH2 minus. Now I know this species carries a negative charge. What we know is anything that carries a negative charge, anything that carries a negative charge first has a potential to act as a base, or as a nucleophile, it has first potential to act as a base, then only as nucleophile. So if I say the basic difference between this species being acting as a base or as a nucleophile is, the fundamental condition for anything to act as a base or nucleophile is same, that it should have one unshared pair of electron at least. If these electrons pair are donated to an H positive, then this species will be called as base. Whereas if the donation of electron pair of this species happens to anything other than proton, let's say a carbon center, then this species will set to act as a nucleophile. And in a species, if there is a possibility that CH3CH2 minus can donate its electron to a proton, and there is a center which is carrying the positive charge, then we know acid-base reactions are faster than your nucleophilic electrophilic reaction. And that is the reason why this negative charge will first try to act as a base and then only as a nucleophile. So using this, what we can do is, I am having acetylene derivative, which is CH3, C triple bond CH. Now, one thing that you had learnt in hydrocarbons specifically was the acidic nature of alkynes. That terminal alkynes have an acidic proton. That is the reason why when I am going to Grignard reagent, which I can assume it as a source of carbon ion, I can say this negative charge is going to pluck out this H positive. And if it is going to pluck out this H positive, both the electrons will be donated on carbon of the triple bond. So it will result into the formation of CH3, C triple bond, C minus, plus CH2 minus after taking a proton will become CH3, CH3, which is nothing but your C2H6. So here you are having C2H6, whereas this can be said to be your compound A. This compound is then treated with CO2. So if I write the structure of CO2, carbon has two multiple bonds with oxygen. And due to the difference in electronegativity, this carbon is said to carry a delta positive and this has a delta negative. This can act as a nucleophile. Here you have the center of electrophile. Then the attack will happen between a nucleophile and electrophile, and the electrons pairs will move on oxygen. If that happens, you can write what will be the next species. So it's going to be C, O minus double bond O. And the last step which is given is actually the workup step to write the neutral product, or you can say it will be the protonation, resulting into CH3C triple bond C, C double bond O, OH. Let me see which option matches this. So as you can see, triple bond will be intact, so you can remove this option. CH3C triple bond C, COH is our answer. If you talk about this, this is the intermediate that forms here. This is actually our A. So if you talk about what is A, option 2 is actually A. What is B? Option 3 is actually B, whereas 1 has no relation with this question. So answer will be option 3 for this CH3C triple bond C attached to carboxylic acid. So how will you convert butane to on to propanoic acid? So what is butane to on? Let me write it. This can be said to be butane 2-on, which is actually a methyl ketone. So this is actually a ketone. So if I am reacting it with Tollens reagent, Felling's reagent, or Benedict solution, these all are mild reducing agents, mild oxidizing agents. Since they are mild oxidizing agent, they do not affect your ketone and hence no reaction. Because you are actually talking about converting a carbonyl compound to a carboxyl group, or basically from aldehyde ketone to carboxylic acid, that step is going to be oxidation. Though these reagents are oxidizing in nature, but they happen to be mild oxidizing agent, and they are not strong enough to oxidize your ketone, and that is why they act as a differentiating reagent between aldehyde and ketones. Aldehyde being the more easily oxidizable species are easily oxidized using this mild oxidizing agent and get converted into carboxylate, whereas on ketone they don't have any effect. If you observe one more thing clearly, then you will find out that butane 2-one can also be said to be a methyl ketone. It has a CH3 group attached to it. Now if I am treating it with NaOH and I2 and later by protonation, then you should understand that this is a methyl ketone and it is capable of undergoing haloform. In haloform reactions, what happens is the bond between the methyl group and CO will break. This carbon will be oxidized to carboxylate, whereas this CH3 group will be converted into ido form, CHI3. And this I negative charge species, as I said, the medium is basic, so you cannot write your acid in the protonated form. So adding an acid will convert it into C double bond OH, which is actually the propanoic acid. So using haloform test, we can actually convert butane 2-one into propanoic acid. So the answer will be 3. I am not writing the mechanism as this reaction is a part of carboxylic aldehyde and ketone chapter, and there you must have surely learned how to write the mechanism. Next is RCOH with N3H leads to RNH2. This reaction is called, so this reaction is actually Schmidt reaction. So if I write what is Schmidt reaction, in Schmidt reaction you have a carboxylic acid. Let's say if this carboxylic acid has the number of carbon atoms is equal to N. Then if you treat it with hydrozoic acid, hydrozoic acid here will be N3H in the presence of concentrated sulfuric acid, then you are going to get primary amine with number of carbon atoms is equal to N minus 1, as one of the carbon of the carboxylic acid groups leaves as carbon dioxide. So let me write the mechanism for you. I will write the one which will be most easier for you to understand. Let's say this is my hydrozoic acid. If this is hydrozoic acid, I can assume that it will dissociate into azide ion plus H plus. Azide ion, if I write, it is said to have needle-like structure like this. Now you should know that nitrogen with 4 bonds will carry a positive charge and nitrogen with 2 bonds will carry a negative charge. If you see the overall charge, plus and minus will cancel out each other, so you will be left with overall -1. That is why N3 is written as N3 minus 1. So what we can do is, you can have RC double bond OH. This RCOH can be assumed to be protonated by the acid. Now this H plus, your wish, you want to consider this H plus is coming from hydrozoic acid, that is also okay. Otherwise you are using concentrated sulfuric acid, that will also work. So here the first step that will happen is the protonation of this OH. So it will become RC double bond O, OH2 positive. Why are we protonating this OH? You will see right after when we are going to attack azide ion. When I am going to attack azide ion, you know, it will undergo nucleophilic acyl substitution via the formation of a tetrahedral intermediate. From this tetrahedral intermediate, when this will come back, the water will leave, as that is a good leaving group. And the protonation of OH was actually done to make OH a good leaving group. So you will be having RCON3, which is acyl azide. This acyl azide structure, I can also write it as RC double bond O, N double bond N, double bond N minus plus minus. Sorry, this nitrogen has 3 bonds, so this will be neutral. You can write another resonating form in this. This bond comes here and this electron pair moves on nitrogen. So the other structure that can be written for this will be RC double bond O, N minus N plus triple bond N. Now this actually undergoes a rearrangement where this bond shifts in between carbon and nitrogen. Let's say this is the first thing that happens. When this bond will shift here, carbon will have 1, 2, 3, 4 already bond, and when you are making the 5th bond, carbon we know cannot make 5 bond. So this alkyl group taking both its electron will move to nitrogen. Let's write it as 2. That is, when this comes here, this bond breaks and moves to nitrogen. And when this bond will be moving to nitrogen, the N2 will leave, which is attached to N. Let's say this is 3. So shift this bond here, then this bond will break. When you will break this bond and attack here, this bond will break. So from this species, the N2 will leave, one of the world's best leaving group. Or you can say the driving force, this rearrangement can be the leaving of N2 group. So what will happen is, you have a carbon which is attached to double bond O. There was a single bond between nitrogen, which has now converted into double bond because you shifted it here, and this has moved an alkyl group here. This, what you can do is, you can do acidic hydrolysis, you can do basic, your wish. So if I add H plus water, you know how to do hydrolysis, right? If I am breaking this bond, I know this will be delta positive, this will be delta minus. So if I orient water molecules, this will be OH, H, and this will be also be OH, H. So breaking this bond, this part will give me H2CO3, or you can say this part will give you C double bond O, OH, OH, which is H2CO3. Carbonic acid we know is not stable, so it will decompose into water and CO2, whereas this part will give you R, NH2. So you will get a primary amine CO2 plus water in the Schmidt reaction. So as you can see, you are having a hydrozoic, you are having a carboxylic acid with hydrozoic acid. In the presence of concentrated sulfuric acid, you are getting a primary amine. You are getting carbon dioxide and nitrogen gas is liberated. This reaction is Schmidt reaction. Curtius reaction is exactly the same reaction, but the difference is it happens with acyl azide, it happens with acid chloride and azide ion. Riemann-Tiemann reaction, you know, is actually used for phenol, wherefore from phenol you prepare salicylaldehyde using CHCl3 in the basic medium, whereas Ullmann reaction you have studied in the alkane hydrocarbon chapter for the preparation of alkane. So our answer here is Schmidt reaction. So this reaction was something that we left. It's not very important from your exam point of view. That is the reason I did not discuss it in the main theory. If you want, you can go through the mechanism. Next is, this reaction is again a part of the aldehyde ketone chapter. So we are having an aldehyde. We know the reactivity of carbonyl compounds is also due to the electrophilic nature of this carbonyl carbon. HCN, you know, can split as H positive plus Cn minus. So Cn minus here, if acts as a nucleophile, will attack this center. This bond will move on oxygen as carbon has to maintain tetravalency. So CH3, CO minus, HCN. This O minus can take out a proton from the solvent, or you can say this H plus is there, so this will be protonated, and what we will get is CH3, C, OH, H and Cn, which later is undergoing hydrolysis. So this is our A, and if I do hydrolysis of this using acid or base as a catalyst, then I know nitrile group will be hydrolyzed to carboxylic acid. So what will be the change? Here this will be OH, H, and this will become C double bond OH. If you check the beginning part where I said remember the nomenclature of common names, then you will understand that this compound was given as lactic acid. So the answer here will be lactic acid. Carboxylic acids have higher boiling points than aldehydes, ketones and even alcohols of comparable molar mass, a statement directly from NCERT, and this is due to the formation of intermolecular hydrogen bonding. So the answer is formation of intermolecular hydrogen bonding, a question directly out of NCERT. Next is, which of the following acids has highest pK and lowest K value? Highest pK means weakest acid. We have already studied the effect of substituent on the acidity of carboxylic acid. So if we see that nitro group is an electron withdrawing group, Cl is also exerting minus I and plus M, minus I and plus M, in which inductive effect for halogens is said to donate. So here also it's minus I, and here it is normal benzoic acid. As we all know that carboxylic acid, after losing a proton, will be converted into carboxylate anion. That carboxylate anion is stabilized by resonance, which will be the stabilizing factor in all these cases. So what we can say here is, this carboxylic acid, since it's not having any electron withdrawing group attached to it, will happen to be the least stable carboxylate anion, and hence, since the stability of carboxylate anion is less, acid will also be less acidic. So this will be our answer. So answer for this question will be option A. Next is, if you notice here, this question is from the last part of the theory which I discussed, which was based on heating effects on hydroxy acids, where we had discussed alpha, beta, gamma, delta hydroxy acids, what are their products on heating. So if I say you have a carboxylic acid, if I label the carbon, this carbon happens to be the alpha carbon. Alpha hydroxy acids on heating forms lactides, which you can see is option 3. So this is directly from that theory part. Heating effects on alpha hydroxy acids leads to the formation of lactides. Next is, in the reaction of CH3, CH2, COH with CH2N2 forms an ester. The reaction intermediate is. For this question, if you look into the mechanism which is given is CH3, CH2, COH. We know carboxylic acids have an acidic hydrogen, and if I write the structure of diazomethane, I can write it as CH2N2. Again, nitrogen with 4 bonds carrying a positive charge. With 3 bonds, nitrogen is neutral. With 2 bonds, nitrogen will carry 1 negative charge. Since this is again carrying a negative charge and this is an acid, so here the first reaction that you can expect is an acid-base reaction, as this hydrogen is acidic. So it will result into the formation of CH3, CH2, C double bond O, O minus. So you will form carboxylate anion plus CH3, N2. If you remember, a few minutes before I said that N2 happens to be one of the world's best leaving group. That is the reason why this O- can attack at this center and N2 will leave, and this will be an example of typical substitution reaction where what will happen is you will have CH3 CH2 C double bond O CH3 plus N2. So here what we have done is we have actually formed ester from the carboxylic acid using diazomethane. This reaction I had not discussed in the main theory as it's not directly given in NCERT, but here you can learn how the reaction happens. And as we can see in this reaction, none of the intermediate forms, neither nitrene, carbene, carbanion or carbocation forms. So basically this question is not relevant, but here if you have to give an answer, then if you study carbenes, then one of the reactions for generation of carbene is the heating of diazomethane. Heating of diazomethane will lead to the formation of carbene. So that might be the reason if you have to choose any reagent here, any intermediate, you can go with carbene. Otherwise, no intermediate of that kind forms in this particular reaction. So if you have to answer, go with the carbene, otherwise not a relevant question. Salicylic acid on reaction with aqueous Br2 gives. So again here the common names becomes most important. So here salicylic acid will be orthohydroxy benzoic acid. This will be OH and this will be COH. If you are treating it with bromine water will actually exist as HOBr plus HBr. So it undergoes disproportionation reaction and this gives a more electrophilic bromonium ion. So bromine water idea is using to produce a more electrophilic bromonium ion. OH group, as we know, is a ring activating group. So it makes the benzene ring more electron rich, therefore promoting it to undergo electrophilic aromatic substitution. That is why phenol is actually more reactive than benzene towards electrophilic aromatic substitution. And since it is ring activating, this group has to be ortho-para directing in nature. That means it will direct the incoming electrophile at positions ortho or para relative to each other. So we know this is the ortho position, this is the ortho position, and this is the para position. So what happens in this case is due to the increased reactivity of benzene ring due to the presence of this activating group, the tribromination happens. That is a white solid which is 2,4,6 tribromo phenol forms. And if we can notice something interesting here, this COH group has been also replaced by a bromine atom, and that is what has been actually observed. If this is a COH group or a sulfonic acid group, you are supposed to do the same thing. The question has been already asked in JEE Mains also. So you can mark it as a star, an important reaction where if you were having a para hydroxybenzoic acid or orthohydroxybenzoic acid, you are doing bromination using bromine water, then it leads to the tribromo substituted product in which if COH or SO3H group is present, they also gets replaced by the halogen. So using that idea, our answer will be option 4. Next is, in which of the following reactions the number of carbon atoms does not decrease? Reaction of carboxylic acid with hydrozoic acid in the presence of concentrated sulfuric acid is Schmidt reaction. If you remember, in Schmidt reaction, the number of it is used for the formation of primary amine from carboxylic acid with one carbon less. Heating of beta keto acid, they undergo decarboxylation. I have discussed in detail the mechanism also. So in this case also, decarboxylation happens and you will get one carbon less. Hoffman-Boehmite reaction is also used for the synthesis of primary amine with one carbon less. So basically, if you remember, this is RCONH2, an amide, and when it is treated with bromine in KOH, then you have been taught to write the final product as remove this CO and directly write RNH2, whereas this CO leaves as CO2, which reacts with KOH to form potassium carbonate. Electrolysis of an aqueous solution of potassium salt of propanoic acid. This is actually Kolbe's electrolysis. Now in this case, if you remember, I had discussed the mechanism also, that here we form an alkane. Which alkane? Which contains twice the number of carbon in alkyl part of the acid. So in this case, if the question is from the starting material, which of the following reactions in which the product has more number of carbons, then the answer will be option 4. Here also the carbon atom decreases because here also reaction goes by decarboxylation, but since the final alkanes contains twice the number of carbon atoms that was present in the alkyl part, answer given is 4. Mechanism for electrolysis of an aqueous solution, I have discussed, this I have discussed, this I have discussed mechanism. This reaction you are going to learn it into the amines chapter, but I have given you the hint how it exactly happens. Next is formation of the following is correct statement. Formic acid reduces HgCl2 and tolerance reagent. That's a true statement because formic acid is said to have some of aldehyde part. That is why formic acid reduces tolerance reagent, Felling's reagent, and it shows all those tests. Monocarboxylic acids except formic acids and esters are functional isomer. Yes, that is also true, that carboxylic acids and esters are functional isomer except formic acid, because for formic acid you cannot make an ester. Whereas at least for acetic acid, if you are writing this as an acid, you can write it as an ester also. So yes, they are functional isomer. Now the next thing is the carboxyl functional group is present in aspirin. Now you may or may not know the structure of aspirin, but since you know the above two are correct, so the answer will be all of the above. But you should know what is aspirin, as this comes as a part of the Riemann-Tiemann reaction. When you take phenol and you treat it with CHCl3 in the basic medium, you end up with the formation of OH CHO, which is salicylaldehyde. If we have learned another variation of it, which is Kolbe-Schmidt reaction. Kolbe-Schmidt reaction involves its treatment with CO2 in the basic medium, and then later you can do protonation where you get salicylic acid. OH, COH. Or this can also be achieved instead of using CCl4, CHCl3, if you are using CCl4 in the basic medium, this will also give you salicylic acid. Now this salicylic acid, if you are going to treat it with acid halide, that means you are going to do acetylation, then the OH group will get acetylated and it will become OCO CH3 with COH, which is actually your aspirin. So yes, aspirin does contain a carboxylic acid group. So the answer here will be all of the above. Benzoyl chloride is prepared from benzoic acid by, we have already come across this question, that is using thionyl chloride or PCl3 or PCl5, out of which SOCl2 is preferred as the other products are gaseous, so no separation of product is required. Next is, which of the following is the correct acidic strength order? So if you see, the acidity can be answered on the basis of the stabilities of conjugate base. So if I write the corresponding conjugate base, we'll see what exactly happens. So in this case, the conjugate base will be CO minus. We know this carbon is sp hybridized. Percentage S character is 50%, and we know percentage S character is directly related with electronegativity. Whereas in the other case, it is CH2 double bond C, C double bond O minus. And in the last case, it is CH3 CH2 C double bond O minus. So here you can actually see the effect of hybridization. Here carbon atom is sp2 hybridized, here it is sp3 hybridized. Percentage S here is 25%, percentage S character here is 33%. So we can say carboxylate anion in all the above cases resonance stabilize. So that stabilizing factor is same in all the three cases. What is the effect of substituent here? If I have a more electron withdrawing substituent, then that will stabilize my carboxylate anion more and hence will increase acidity more. As I can see, in this case the substituent has a carbon atom which is sp hybridized, which has 50% S character. And we know as percentage S character increases, electronegativity increases. So I can say this substituent will have the most minus I effect, and therefore their carboxylate anion will be most stable. Thereby, if the stability order is this, then the acidity order will also be that. So you can say this will be our answer. Next is COH NH2. Now for second case, nitrogen here will be applying plus M effect and minus I effect. Plus M effect is going to be dominant. So this will be overall an electron donating group, whereas from meta position it can only apply minus I. As we know, acidity increases with negative effects, or you can say with electron withdrawing, or you can say acidity increases with electron donating. So what we can say here is that acidity increases if there are more number of electron withdrawing groups, or acidity decreases if electron donating groups are there. Since here NH2 group is showing overall electron donating effect, it will increase the negative charge density, will decrease the acidity. Therefore this order is not correct. Whereas if we talk about OCH3 here, this is at meta position, so can only apply minus I. Whereas OCH3 will apply plus M and minus I. Plus M is going to be dominant, so we can say this group will particularly act as electron donating and this will act as electron withdrawing. And as we know, electron withdrawing group increases the acidity, so answer here will be both 1 and 3. The second option is not correct. Next is, which of the following reaction is suitable for the conversion of an amide to amine? If we can see here, this reaction actually corresponds to where an amine is prepared from an amide containing one carbon atom less. And if you remember, I just told you this reaction is Hofmann-Boehme reaction. Carbylamine reaction actually converts primary amines into isocyanides, so this cannot be the reaction. Kolbase-Schmidt reaction is actually this reaction, which is preparation of salicylic acid from phenol, so that also does not apply. Whereas Koch reaction is again for the preparation of carboxylic acid, not directly there in your syllabus. Next is an amide given with P2O5. So if I see what happens to an amide when it is treated with P2O5 or let's say SOCl2, here they actually kind of act as a dehydrating agent where there is a loss of water and amides are actually converted into nitriles, RC triple bond N. So you can say this is an amide, and amides on dehydration will be converted into nitriles, C triple bond N. Now one reaction which you must have learnt in aldehyde ketone chapter, that is when you are having a nitrile, and to this if you are adding a Grignard reagent, let's say CH3MgBr, we know this is the electrophilic center, this is the negative charge, so the CH3 minus can attack here, one of the pi bonds will move on nitrogen, so this will become RC triple bond N minus and CH3, and this was later hydrolyzed to ketones. So this will become CH3CO plus N minus will part get converted into NH3. So we know addition of Grignard reagent to an alkyl nitrile will result into the formation of ketone. That is, this RC, the triple bond between them will break and this will be converted into ketone. So if I have to write here that after adding Grignard reagent, what will happen is then this will be converted into ketone, COCH3. Next reagent, if you see, you are taking a base along with iodine, so this will result into the formation of haloform reaction. In haloform, what happens is, I have already told you, if it is a methyl ketone, then this carbon will be converted into CHI3, whereas that carbon will be oxidized to carboxylate. Since it's a calcium salt, the final carboxylate will have this structure. Since calcium has a valency of 2, you can say your final carboxylate will be C double bond O minus. This will be 2 times calcium. So this is our C. Now this reaction again you have learnt in the preparation of aldehydes and ketone, which will be dry distillation of calcium salts of fatty acids. In dry distillation of calcium salts of fatty acids, what happens is it forms either the ketone or aldehyde. If the salt of calcium which is heated is anything other than calcium formate, then it always results into the formation of ketone. Whereas if calcium formate is treated with any other calcium salt, then the product will be aldehyde. Since we do not have calcium formate here, we are only having calcium salt of some other acid, that is why it will result into the formation of ketone. And the ketone part will contain this alkyl part on either side. So here the product will be CO, again with the 5-member ring. Or you can say, if the calcium salt is CH3CO minus, let's say acetate ion 2 times calcium, then if you are doing dry distillation of this calcium salt, again here it will be ketone. Which ketone? In which this alkyl part will be there on either side. So I can say, if I do the dry distillation of acetate salt of calcium, then acetone will be the product. Or if this part is RCO minus, then ketone will have RCOR. So since this has a 5-member ring, the ketone will be formed which has 5-member ring on either side. So that will happen to be our option D. So this is actually one of the methods of formation of aldehydes or ketones by doing dry distillation of calcium salts. So if you have seen the overall sequence of reaction, what has happened is, first we took an amide and we used the dehydrating agent. Dehydrating agent in the sense, you can say, let's say this I am writing it as NH2. So you have removed H2O and you form triple bond in between carbon and nitrogen. Or with SOCl2 or PCl3, like amides forms nitrile. So after forming nitrile, you are adding Grignard reagent followed by hydrolysis. We know that when you add Grignard reagent to a nitrile, it actually results into the formation of ketone. So what we did is we formed ketone. When we formed the ketone, we realized that we are having a methyl ketone, and that is the reason this reagent next they gave was a haloform reaction. So once we did haloform reaction, we know the carbonyl part of the ketone gets oxidized to carboxylate, and the methyl part gets converted into the haloform, which will be CHX3. Since it was a salt of calcium, so we wrote it as that. And when you heat calcium salts of fatty acids, it results into the formation of aldehyde or ketone depending on which salt of calcium you are heating. If you are heating any salt of calcium which is other than calcium formate, then the product of dry distillation will be a ketone. Whereas if it is heated with calcium formate and any other salt, then it will be an aldehyde. So that was the overall idea of this reaction. So in the following sequence, what is D? As you can see, we are having an alkyl benzene, and this represents oxidation. So we can assume that they are actually asking us to oxidize alkyl benzene into carboxylic acid. Next reagent looks very familiar, which is conversion of acids into acid chloride. So this will become COCl, and then it is treated with sodium azide. After treatment with sodium azide, you know, a nucleophilic substitution, acyl substitution will happen here, where you will result into the formation of acyl azide. If you remember something here, then this is what I formed in the Schmidt reaction also. Schmidt reaction starts with carboxylic acid and hydrozoic acid, whereas Curtius reaction starts with acid halide and sodium azide. So if I am heating this, and if you remember what formed here was, let's say this is pH, this is CO, and if I write the azide structure as N double bond N plus minus. So I wrote one of the resonating structure in which I donated these electrons on the nitrogen. So it becomes N minus plus triple bond N. Now if you are heating it, these are the things which are happening. So this can donate here, let it be 1. This bond will break, let it be 2, and then nitrogen leaves. So the intermediate that we formed was of something of this type, if you recollect, which is phenyl, and this group is isocyanate. So this intermediate is known as phenyl isocyanate, which on hydrolysis will give you primary amine and carbon dioxide. But since we are not doing hydrolysis, we are stopping just after heating, so it will be phenyl isocyanate. So this intermediate which is formed after heating is isocyanate. This, if another step was given, that is hydrolysis, then you could have formed your pH NH2, as hydrolysis will break this bond and you will get carbon dioxide. So for this question, answer will be phenyl isocyanate. Next is silver benzoate reacts with bromine to form, and if you see, it's a silver salt of carboxylic acid. So it's Hunsdiecker-Borodin reaction, for which mechanism I have already discussed, and here also you learned that it is actually used for the preparation of alkyl or aryl halide containing less 1 carbon than the parent acid that you have started with. So this will be treated with bromine in carbon tetrachloride and will lead to the formation of aryl halide here. Mechanisms for this I have already discussed, so that will leave us with option 4 as an answer. Next is propanoic acid reacts with bromine red phosphorus, forms a dry bromo derivative. Its structure would be, so if you see, bromine in red phosphorus along with an acid is an example of HVZ reaction, and HVZ reaction is actually used for bromination at which position? Alpha position. So if I know the naming. This is alpha position, this is beta position. So if I am using it with X2 in red phosphorus, then the two halogens will be put at alpha position. So if you just recollect that what is HVZ reaction, you will understand your dibromo derivative is this what they are talking about. Next is, which of the following is the nitration product of this ring? Now I know for this thing you are only supposed to look at the key atom which is directly attached to your ring. Let's say this is ring 1 and this is ring 2. While deciding NO2 will go on which ring, you need to look at the key atom or the atom which is directly attached. So I am going to mark it as star 1 and this as star 2, as this is the key atom attached to ring 2. This is the key atom which is directly attached to ring 1. If you talk about this group happens to be a minus M group. And minus M groups, you know, will happen to be electron withdrawing group or ring deactivating. Or you can say, since the ring 1 is attached to an electron withdrawing group or ring deactivating group, this ring will have less electron density and will be less reactive towards electrophilic aromatic substitution. Whereas if you look at the atom which is directly attached with the ring 2, you will observe that it is an heteroatom which contains a lone pair of electron. And we know this lone pair of electron can be donated into the ring due to its plus M effect. If it donates electrons into the ring, it will increase electron density in the ring, thus activating it towards electrophilic aromatic substitution. Since we are talking about nitration, so NO2 plus will be the electrophile. An electrophile is a species which likes more electron density. So as you can see, ring 1 and ring 2, which one has more electron density? Due to an electron donating group attached to ring 2, this will be having more electron density, and that is the ring where NO2 will go. So your answer will be option 3. Because it will not go on both of them. Here it is going on ring 1, which is actually deactivated, and again this is also wrong. So first of all, what we have to decide is which ring will be nitrated, and after that ortho or para. Then always whenever you get substrate like this, then due to steric crowding at ortho position, ortho positions will be sterically crowded. That is why attack will happen at para position. So that was the logic how to attempt this question. Next is, in the reaction C8H6O4 gives X and Y. The product X is. Now if you recollect, I gave you the similar question while discussing the reaction of carboxylic acid with ammonia, where phthalic acid was actually treated with C8H6O4. So this phthalic acid, if you are heating it, if you see this is 1, 2, 3 and 4. 1 for acid on heating, I have already told you what they do is, on heating they will cyclize to form the anhydride. So we will form what is phthalic anhydride. This phthalic anhydride, when later treated with ammonia, if it is excess of ammonia, then this bond will break, this bond will break, this will be converted into amide, and this will also be converted into amide. But right now we are only sticking with C8H6O4 is phthalic acid, which is a 1,4 acid. I have already discussed what are the heating effects on 1,4 acid. So they cyclizes to form the anhydride. So this is going to be X, and our answer will be phthalic anhydride. Next is the reactivity order of carboxylic acid derivatives during nucleophilic acyl substitution. This also I discussed. This was the last part of our theory, in which acid halides are the most reactive, followed by acid anhydrides, then esters, and then amides, which will give us option 2 as an answer. Again, the compound that undergoes decarboxylation most readily under mild condition is, I told you, when the two acids will be having 1,3 relation with respect to each other. It can be 1,3 diacid or it can be a beta keto acid. They readily undergo decarboxylation on heating. Here if you see the relation, this is 1,4. 1,4 will actually form the anhydride. This is 1, 2, 3, 4, 5. 5, they will also form anhydride. This actually happens to be alpha, beta keto acid. So this will decarboxylate, whereas this is alpha, beta, gamma. So no decarboxylation in this case. So beta keto acids, as we know, are the substrates which undergoes decarboxylation very easily, and that is what the only thing you had to look there. Next is the correct order of strength of carboxylic acid. So here we have to look at the substituents. So group O, if you look here, this O is actually exerting its minus I. Here also this O is exerting its minus I. Inductive effects we know are actually distance dependent effect. So electron withdrawing group nature of O will be more when it is closer, which is in this case, whereas in this case inductive effect of oxygen will be less as it is far from the carboxylic acid unit. That is the reason why second will be more acidic than third, which will be more acidic than 1. So the answer will be option 3 based on inductive effect or the effect of substituents on the strength of the carboxylic acid. Next is an organic compound A with molecular formula C8H16O2 hydrolyzed with dilute H2SO4 to give a carboxylic acid and alcohol. That means it has to be an ester. Let's call this ester as RCO R'. When I hydrolyze an ester, let's say using dilute H2SO4, it's actually giving me an acid. An acid will be RCOH, let's say this is A, and an alcohol which is R'OHB. They are saying this alcohol R'OH, if I oxidized it with chromic acid, let's say CrO3 in H2SO4, it was converted into acid, and this acid was actually same as B. That is, C on oxidation gives, for example, if I am having an alcohol as RCH2OH, it has to be a primary alcohol only, because primary alcohol only on oxidation will give carboxylic acid. So this will be RCOH. That is, if primary alcohol, the number of carbon atoms are actually N, then in the acid also the number of carbon atoms will be N. So if they are saying that an ester on hydrolysis gives two products, which is A and B, this is an organic compound A. So there is a slight problem in nomenclature. So this is A, which on hydrolysis gives B and C. This C on oxidation produces an acid which is same as B. So from this, what I am trying to tell you is that if alcohol has to form this acid, then the number of carbon atoms in both of them should be same. Or what I am trying to say is this R and this R' part should have the same number of carbon atoms if this scheme is to be satisfied. Now let me actually show you by taking one which is symmetrical. This is 1, 2, 3, 4. 4 carbons on one side, and alkoxide part will also have 4 carbons. So if I write reaction sequence for that, you are having an ester CH3, CH2, CH2, C double bond O, O, CH2, 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 CH3. I know ester hydrolysis H plus water is simply the breaking of this bond. This is delta positive, this is delta minus. Orienting the dipoles of water will give me CH3, CH2, CH2, C double bond OH, because there are 1, 2, 3, 4 carbon, plus other side you will get HO, CH2, 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 CH3. So this is A, and if this is B and this is C, I know C is a primary alcohol, and if I do its oxidation using John's reagent, I will get a carboxylic acid, which will be again butanoic acid. So for this acid to be same as this one, what I am trying to tell you is the number of carbons in the alcohol part should be same as in the acid part. That was the logic of choosing which of the following here will be our answer. So you had to choose that R and R dash should have the same number of carbon atoms, then only this scheme will be validated. So that leaves us with option 2 as an answer. Next is acrylic acid on reduction with lithium aluminium hydride gives. So first thing we need to know what is acrylic acid. So if you have ethene molecule and if you put COH there, this will become our acrylic acid. And you know, lithium aluminium hydride reduces carboxylic acids into alcohols. So our product will be CH2OH, which leaves us with option 3 as an answer. Next is malic acid is more soluble in H2O and fumaric acid at constant temperature. So first you should know that malic acid and fumaric acid are actually geometrical isomers of each other. Malic acid happens to be cis dicarboxylic acid, trans dicarboxylic acid is your fumaric. So this is fumaric and this is malic acid. If I talk about the polarity of these two, then if you do the dipole moment, this carboxylic will have a resultant dipole moment in this direction, whereas this majority of the dipole moments will be cancelled in this case, but still fumaric acid won't be non-polar. Keep that in mind. Fumaric acid will also be polar but comparatively less polar. So if I talk about which is more polar, then you will find out that malic acid is more polar than fumaric acid. Since we know with the general idea like dissolves like, so polar solvents will dissolve polar compounds. And since malic acid is more polar, we can say malic acid is more soluble in water than fumaric acid. If I compare Ka1 and Ka2, that is the first acid dissociation constant and the second acid dissociation constant, then the first acid dissociation constant is greater for malic acid, whereas the second dissociation constant is greater for fumaric acid. That is, this statement that Ka2 of fumaric acid is greater than malic acid is also true. Again, how to understand that? I have already told you, whenever you want to compare the stability, whenever you want to compare the acidity of an acid, always compare the stability of its conjugate base. So I can say this is the conjugate base which forms from malic acid after losing an H positive. As you can see, they are in perfect alignment to form intramolecular hydrogen bond. So you can say the conjugate base in malic acid is stabilized by hydrogen bonding, whereas no such stabilization intramolecularly is possible in case of fumaric acid, which is like, because they are pointing opposite to each other. So here conjugate base cannot be stabilized by intramolecular hydrogen bond. There it can be stabilized, since after losing the first H positive, malic acid has a more stable conjugate base. More stable the conjugate base, more will be the acidity, and that is the reason why malic acid first Ka value is more than that of fumaric acid. When you talk about losing the second one, let's say this was the first Ka1, now you are talking about Ka2 losing the hydrogen which is attached to another carboxylic acid also. So here what you will have is, here you have C double bond O minus, and here also you will have C double bond O minus. So this will be the conjugate base. There are two ways to understand why this conjugate base is not more stable. The first reason will be the repulsion between these two, negative charge electron density, because they are cis, so they will be closer, so there will be repulsion which will make this conjugate base less stable. Plus, in addition to break this OH bond, you have to break this hydrogen bond also. So here I can say you are actually supposed to break two interactions for make the hydrogen to leave the molecule. Whereas when you look at fumaric acid and you want to lose one more hydrogen, which will be represented by Ka2, that will be C double bond O minus, that was formed after first losing H positive, and this will be formed after second. So if you see here, since two carboxylate anions are far from each other, there will be less repulsion, by which you can say they will be more stable. So you can say conjugate base which is formed after losing the second proton is more stable in case of fumaric acid due to less repulsion. Or you can say you only need to break one interaction to make this hydrogen leave. Whereas in case of malic acid, you have to break two interactions. Since you have to break two interactions, hydrogen loss will be difficult there. That is why if we are talking about the first and the second dissociation constant, the first dissociation constant is more for malic acid. That means tendency to lose the first H positive is more for malic acid, whereas tendency to lose second H plus is more for fumaric acid. So if you talk from the first H plus losing, malic acid will be more acidic than fumaric, whereas if you are talking about losing the second H plus, then fumaric acid will be more acidic than malic acid. Next is orthonitrobenzoic acid is stronger than paranitrobenzoic acid. Since you know already these two statements are correct, so the option has to be all of this. Otherwise, this also you can remember it as ortho effect. Ortho substituted benzoic acids are more acidic than its other derivatives. Next is when benzaldehyde is treated with concentrated NaOH solution to give the products A and B. The product A can be used as food preservative and B is an aromatic hydroxy acid in which OH bonded to an sp3 hybridized carbon. The products A and B are. So here the moment you should see benzaldehyde, all reactions of aldehyde with no alpha hydrogen should click into your mind. So this is an aldehyde with no alpha hydrogen and you are using concentrated NaOH. So concentrated NaOH with aldehyde having no alpha hydrogen will undergo Cannizzaro reaction. Cannizzaro reaction we know is an example of redox reaction or also a disproportionation reaction where this carbonyl carbon gets reduced and oxidized. So that carbon will be oxidized to carboxylate CO minus plus will be reduced to alcohol. So here as you can see, OH is bonded to sp3 hybridized carbon atom. Here OH is bonded to sp2. Here also OH is bonded to sp2. Here also OH is bonded to sp2. This is the only case where OH is bonded to sp3 hybridized carbon. So our answer will be option 2. So these were the questions that we had for in carboxylic acid chapters. In case you have any other doubt, you can contact me on this number. Thank you.